I think recording is on. Phil, do you want to start? Thanks.
All right. Well, thanks everyone for joining for this edition of the RL Theory Seminar. This week we're very happy to have Jongha Ryu, who's a postdoctoral associate at MIT Electrical Engineering and Computer Science. He received his PhD in electrical and computer engineering from UCSD, and his research focuses on statistical and mathematical foundations of scientific machine learning, with work on neural spectral methods, score-based generative modeling, and off-policy or in sequential decision-making problems. So yeah, John, take it away.
Yeah, thanks for inviting me. So I'm really excited to have this opportunity to present my work in front of this theory audience. So so today I'm going to talk about our work on offline contextual bandits with some improved second order bounds. So I'm going to talk about what these betting and freezing are in the talk. Right. So and this was presented at this year's COLT. And this is a joint work with Jongha, who was at Wisconsin Medicine but joined Meta recently, and Benjamin on undergrad at Cornell, and Guangsong at Arizona. All right, so yeah, let's get started. So I'm gonna start from the very basic setup, such that like people don't get lost. But yeah, please bear with me if these are too basic. Right. So yeah, so we are interested in this contextual bandit setup throughout the talk. So obviously the canonical example is the recommendation system. So there's a set of users and set of items and some recommendation system, which is often called policy in the contextual bandit setup. So a user arrives as a d-dimensional context vector and to the recommendation system. And recommendation system is typically characterized as a conditional distribution over all items. So given the user, it's a distribution over the actions, the items. So A is chosen according to the distribution and served to the user. So it's an action chosen from a finite set. And then the user gives a feedback, like in terms of click or rating, which can be represented as a real value between 0 and 1. Right. So in this contextual bandit setup, the goal is to find the policy that maximizes cumulative reward. So in the literature, under the ideal assumption, people have like studied how we can choose like good policy from the given class by allowing online interaction, meaning like to see whether some policy, how some policy would work in this environment. They deploy this, they assume that we can deploy the policy here and then collect some data and then evaluate that and repeat the procedure. But in practice, this online interaction can be really expensive because of many practical constraints. Like, for example, there can be some system constraints. So system engineers in a company might not like the idea of like changing policies like within short time period. And in a large company, as an organization, there might be some bureaucratic like chain of approvals to deploy new policy and so on, right? And if you think about like fine-tuning your policy on a real-time basis, even if we assume that this can be overcome, if you want to really fine-tune your policy real-time, then you have to get feedback from human at the same pace, but that can be really expensive as well. So yeah, it might sound very trivial, but online interaction is very expensive in practice. So an alternative way is to go offline. Okay, so an obvious alternative of online is to go offline. Right. So what do I mean by offline? So in the contextual bandit setup, here this is exact problem setting. So we're going to assume that there exists some behavior or logging policy pi0 a given x, which generates the offline data, which is which are tuples of context, action, reward drawn from this joint distribution over XA and R, where the action is drawn from the logging policy, and PX and PR given AX are the distributions defined by the nature. Or more precisely, this data is collected by going over this step n rounds for n rounds. So at time t, we observe user xt drawn from some underlying distribution, and the action is chosen from the logging policy by the logging policy, and we observe reward by the reward distribution, which is underlying, which is given by the nature. All right, so in this off policy setup, the goal is to again find the best policy pi hat that maximizes the so-called value, which is defined as the expected reward. So the value of a policy pi is defined as the expected reward under this distribution where the action is chosen by that policy. Right. So this is the off-policy contextual bandit problem. Then what's the challenge, right? At the highest level, so the difficulty comes from the fact that the logging policy is different from the target policy of our interest. More concretely, we can illustrate a challenge with this example. So suppose that at some round t, given context xt, let's say the underlying reward function is deterministic and given as a table like this. Okay, and we can imagine that hypothetically a behavior policy pi 0 chose action 2. So this reward 0.1 is observed. But then the target policy of our interest from the policy class might choose action 3 with high probability. But then this is unobserved, right? So there could be this kind of mismatch in the data in our policy class, and our policy of our interest. And more schematically, we can describe this issue in this visualization. So we can imagine that there exists we can imagine the data space, which is the product space over the context and action. And for a given policy pi, the high probability region in this data space might look like this. But what we are given as offline data might only cover the high probability region with this small overlap. So if such a scenario happens, then there exists a risk of over-optimization, meaning that a low-value policy pi might seem good on this overlap that result in picking up this low-value policy if you just optimize over this offline data. Okay. So this is a very high-level challenge in the off-policy setup. Okay. So we want to deal with this over-optimization in general. Right. So before I go into the detail, I will just briefly overview the landscape of the type of off-policy problems. So there are 3 different categories we can think about. So the first is evaluation, where there is a single policy pi of interest, and the goal here is to estimate the value of pi. This can be typically, thought as like test phase in the supervised learning setup, and there exists a selection problem where we are given a set of finite policies, and the goal here is to find the best policy from the class using the offline data. And typically this will be done with some validation split of the data. So you can imagine that this is an analogous version of the model selection in the supervised learning setup. And the last column is the most difficult setup, where the policy class here is infinite, like you can imagine a policy parameterized by a neural network, then the goal is same as selection, but since the policy class is much larger, the problem becomes much difficult. So yeah, so in this learning setup, to argue any theoretical bound, we need to assume some oracle efficiency, like meaning that we need to like hide the optimization complexity to get some bound, and we need to impose some additional assumption on the objective functions in this optimization procedure. Right. So for the rest of the talk, I'm gonna mostly focus on what we can do with the selection problem, and I will briefly touch upon this learning problem at the end. And the evaluation problem can be also tackled by the same technique of selection, but I'm not gonna go into the detail for this talk. All right. So before I go into the selection, is there any question? If so, please let me know. Otherwise, I will proceed. Okay, good. All right, so let's start with the off-poly selection. So if you think about it, the selection problem can be solved in a very straightforward way if we know how to estimate the value function, which maps a given policy to the value using the offline log data. So again, the value is nothing but the expected value of the reward under the policy distribution, target policy distribution. Pictorially, you can imagine that the reward density looks like this. So this is a marginal density over the reward under this joint distribution. And what we want to estimate is this mean of the distribution, right? But the issue is that we don't have access to the samples from this joint distribution. So a natural solution is to introduce this importance weight to change the measure from pi to pi 0. And then invoke the Monte Carlo approximation to get this form of importance weighted estimator or IPS estimator, which are called, by many different names, like even IPW, but they are all the same estimators, which are based on importance weighted reward. Okay, so the nice thing about this is that, this estimator is unbiased, which is good. But now the issue is that the random variable we need to handle right now is not just the reward, but the importance weighted reward. So with this importance weight, the marginalized density induced by this joint distribution now might look like this, while the mean is still here, the same. But the distribution can be potentially unbounded support and high variance. So it depends on the choice of the logging policy. So with some assumptions on pi 0 I given x, we might have some control over the tails or the boundedness, but without any assumption, we cannot say much about the tail of this distribution and the boundedness. Okay. So what this says is that this IPS estimator is unbiased, but could be high variance. So for example, we can think about this toy example here. So let's say we have M policies in the policy class, and these gray dots represent the true values of these policies. And let's say we estimate the value using IPS estimator, and we got these X marks. So if we knew the underlying true values, then we should pick the second one. But since we only have access to this IPS estimates, if you just choose naively based on the estimator, then you will pick the low value policy and the ground truth population limit, but because of the high variance, you might pick this, which is exactly the over-optimization issue. Okay, so we want to get rid of this type of behavior. So how can you do that? So to address this over-optimization, we can implement the standard idea of pessimism. So the idea is that why don't we take into account the variance of the IPS estimator itself? So if we construct a lower confidence bound on the value v pi, then we choose the maximum, the policy that maximizes the lower confidence bound. So for example, like in this case, the lower confidence bound might be constructed like this. Then we can, the previously looking good policy now is discounted by the variance. So we can choose the good policy by pessimism. So we can avoid over-optimization with the idea of pessimism. So good. But I'd like to remark one caveat here, which is that the pessimism doesn't solve all problems of all policy problem, because if the truly optimal policy has a high variance with respect to the offline data, then it might be still not visible during the selection process because of this, noisy, because of the variance introduced by the offline data. But at least what we can prevent with this pessimism is to pick up the low value, high variance policy. Right. So given this idea of pessimism, our contribution in off-policy selection problem is to propose a tight LCB, low confidence bound, that yields probably good selection via pessimism with two desirable properties, which is first, having this variance adaptive property, which I will explain in the next slide. And this can be achieved without any hyperparameter tuning. Okay. All right. So in this slide, I will just highlight what we can achieve theoretically with our proposal. So our proposal is called pessimism by semi-unbounded coin betting. I'm going to explain what this means. But at a high level, what we propose is a new lower confidence bound based on some ideas, some combinations of the betting technique and universal portfolio, which I will elaborate soon. And let's say we have such a construction, some construction of LCB, then our algorithm is nothing but applying pessimism using that LCBs. Okay, so the main theorem of our paper is the following. So if pi hat is the chosen policy based on our pessimism, then what we can guarantee is that the optimality gap, or the gap between the value of the chosen policy to any other policy, is bounded by this diminishing factor, 1 over square root 1 factor, times square root of r tilde pi star, where this r tilde pi is the importance weighted reward. Okay, so this suggests that this is variance adaptive, and this is variance adaptive. And I'd like to also highlight that this guarantee, this bound, can be achieved without any hyperparameter tuning. And we can make a direct comparison to the prior art, which is logarithmic smoothing by Saki et al. And in their paper, they achieved the bound on the optimality gap with the factor of 1 plus second moment, not the square root of variance. So if you think about the comparison between the square root variance and the second moment, then you can realize that there is a two-step improvement in the sense that the square root of variance is upper bounded by variance, and variance is upper bounded by the square root of, the second moment. Okay. So this is what we can achieve compared to the state of the art. Do you have any question? Please, if so, please let me know. Right.
Yeah, I think so far it's very clear for me.
Okay.
Yes.
Sure. Sounds good. All right. So now let's zoom out a little bit further and look at the literature from the bird's eye view. Then we can summarize the prior works based on the requirements on the boundedness or moment condition for either guarantee or deployment, and whether there exists a rate guarantee or not, and whether the optimality gap is adaptive to which measure. Okay. So the first work you can think of is the empirical Bernstein by Maurer and Pontil. So they require they have some adaptive variance adaptiveness which is desired with rate guarantee, but they require some boundedness or finite moment condition or tail condition on the distributions. And there is a line of recent works. This Oracle efficient pessimism by Wang et al. Actually falls into the category of offline learning or optimization, but I'd like to mention that with the recent work also has this guarantee under some boundedness condition, and this has undesirable worst ratio factor. And more recent works have tried to get rid of this boundedness condition and with some rate guarantee. And this implicit exploration and logarithmic smoothing are the closest ones to our work. But in terms of guarantees, the leading factors are suboptimals. So I'm going to talk about these three works in detail in the next slide. Okay.
Can I ask a quick question, clarification?
Sure. Yep.
When you mention boundedness and moment conditions, you mean on the importance ratios?
On the importance weight or the importance weighted reward.
Okay.
Yep.
Cool.
Yeah. Thanks for the clarifying question. All right. So, okay. So before I compare these, the last three, I will give you a little bit more higher level remarks on the notion of coverage measures. So if you look at the literature on analyzing the optimality gap with the offline data, then the leading factor is typically the discrepancy between the target policy pi and the logging policy pi 0. Okay. So, for example, in reinforcement learning, a more general setup, the notion of worst case coverage is kind of standard because this is the easiest to think about. So meaning the discrepancy measure between pi and pi 0 is oftentimes captured by this maximum, the worst case ratio between pi and pi 0 for all possible pairs of A and X, which is not desirable, which could be very large. And in this line of policy contextual bandit literature, people have proposed different notion of discrepancy measures between pi and pi 0. So this Wang et al. Paper introduced the notion of pseudo loss by replacing this maximum with expectation over px and summation over A. And smooth coverage, the implicit exploration paper introduced the notion of smooth coverage ratio, which can be understood as incorporating this reward and the expectation with respect to the underlying reward distribution on top of the pseudo loss with some smoothing. And the most recent one is the logarithmic smoothing paper, and they capture the discrepancy by the second moment, as I alluded to earlier. And in our case, and like in empirical Bernstein, we captured this discrepancy in terms of the variance of the importance weighted reward. So at a very high level, you can see that over time, the notion of the coverage or the discrepancy measure between pi and pi 0 has been refined from the worst case ratio to the average measure that fully captures the probabilistic nature of the problem setting. All right. Okay, so I'm gonna make a last remark on the direct comparison of these last three works, and then I will give you a construction recipe for our LCD. Okay, so we can make a direct comparison between these three works, and in the previous slides I said the leading factor, the multiplicative factor is second moment and variance, but these were largely simplified to make the comparison simpler. And what we can actually show in the paper is with this smooth notion of second moment and smooth notion of variance, which are written as follows. And this is the same expression for the smooth coverage ratio. This is just a rewriting of this same expression with all tilde pi. And you can see that this is monotonically decreasing because like from pi 0 compared to this and this, you can see that this pi 0 times all tilde was replaced with 1. And since pi 0 all tilde is less than 1, if A is finite, so this is smaller than this. And you can understand the smooth variance as a centered version of the second moment here. So you can argue that this is smaller than this. And since this gamma value is, if you tune it optimally, it should be at the rate of 1 over square root n. So in the asymptotics, you can see that this will go to 0, and this will become the second moment, and this become the variance, as I said earlier. And the last comment I'd like to make is about the tuning of this gamma parameter. So in these IX and LS papers, the gamma parameter needs to be tuned. And if you tune this with an oracle knowledge, like meaning the underlying discrepancy measures, then you can put this factor into the square root. But knowing this discrepancy measure a priori is impossible. So that cannot be done. You can do like cross-validation, but yeah, that's a secondary issue. But in contrast to these frameworks that require hyperparameter tuning, what we can achieve is the square root of this measure without any hyperparameter tuning, because what we deploy in the LCB construction, which is universal portfolio, has automatic tuning feature. Okay, so that's another distinction from these two prior works. Okay, so this was about the technical comparison of our guarantees with respect to the prior arts. And in the next slides, I'm going to talk about the actual construction that gives this like very nice theoretical guarantees. So before I go into the construction, please let me know if you have any question about the guarantees and comparison.
This is a high-level question that doesn't have to do with like your results, but is second moment bounds, like the variance, optimal? Is there a sense in which you cannot get even higher?
Right. Yeah, that's a great question, and we are not aware of any lower bound result. So yeah, right. Yeah, it'll be cool to have the lower bound, matching lower bound, or at least some lower bound. Yeah. All right. Yeah, if there is no other question, I will give the recipe for the construction of the lower confidence bound using the idea of betting. Okay, so for this subsection, let's just focus on like purely building lower confidence bound with the samples from samples of non-negative random variables with unknown mean mu, where for the previous all policy problem, you can just plug in the importance weighted reward in place of YT. Okay. So in this setup, what we want to do is to construct a lower confidence bound, L and delta, which satisfy this lower bound with high probability. So obviously, the most naive attempts would be to just deploy empirical Bernstein. But we can think about, there are two different issues with this empirical Bernstein. So first, theoretically, to analyze this convergence behavior of this lower confidence bound, you need some boundedness or tail condition on YT. And practically speaking, for this bound to make sense, we need at least finite force moment to make this empirical variance to converge to the actual variance. Right. So we want to get rid of all these, complications. So to explain our construction, I'm gonna explain this in three different stages. So the first stage is about the generic framework of constructing lower confidence bound via testing. Okay. So so you can imagine that there exists a non-negative real line, and mu lies on this non-negative real line somewhere around here, where you cannot see it. And to construct a confidence bound, what we want to do is the following. So for each candidate parameter nu, we want to test whether this nu parameter can be mu or not. So how are you gonna do that? So we are gonna do this by some potential function, g and nu, with two properties. So the first property we desire is the decreasing property. So g and nu has to be monotonically decreasing as a function of nu. And the second property we want is that this value of this potential function at the mean parameter mu must be small with high probability. So what I mean by this, so we can be a little bit more concrete. So for a threshold 1 over delta for some value between 0 and 1, we want this value g and mu to be smaller than this threshold with probability at least 1 minus delta. Okay. So suppose that we have access to this potential function, then what can we do? So by the way, this with probability is with respect to the randomness in the samples, in the observations. So given this potential function, what can we do? So since we know that g and mu will be less than this threshold, we can look at this sub-level set, and then we can say that, yeah, mu, this g and mu has to be smaller than 1 over delta, so mu has to be in this sub-level set somewhere. which means that this sublevel set will be the confidence interval for the target parameter mu. Okay? And by the monotonically decreasing property, this confidence set must be like half open interval. So if you consider the infimum, then this will serve as the lower confidence bound of the mean mu. Right. So this is a generic construction of the lower confidence bound from the potential function. And now the question is, how can we construct such a potential function? So the connection of this testing to betting is that we can design a potential function with this desiderata as a wealth function from some betting against the synthetic stock market with design.
So maybe just a naive question.
Sure.
Given the two constraints that you wrote for the potential function, I feel like you could design pretty easily like such a function, like to be less than 1 over delta.
Yeah.
So like, is there another constraint that is not?
Right. So yeah, this is just a generic mapping from some potential function to the confidence bound, and there's no like control over the tightness of the constructed confidence bound, right? So we want the potential function to be as large as possible when mu is less than nu, like at a very high level. But at this point, yeah, this is just a mapping from such a potential function to mu. So as you said, like you can always choose like constant function or yeah, and that will give you a very stupid lower confidence bound.
Yeah. Okay. I see. Thanks.
Right. Okay. So I'm gonna talk about that, the tightness, the choice of the potential function and the tightness of the lower confidence bound after I talk about the betting. Okay. Thanks. All right. So now I'm gonna talk about how to design such a potential function by betting. So I will first give the direct construction of the potential function out of the betting, and then explain how this was constructed from some stock market. So the potential function we can design from betting looks like this. And I'd like to ensure that this satisfies the two desiderata. First, so BT and 1 minus BT is some value between 0 and 1. And then BT and 1 minus BT, both of them will be non-negative, meaning that this factor will behave as 1 over nu. So this is monotonically decreasing in nu as desired. And secondly, if you look at this expression, then we can easily see that this constructed sequence of GT mu is a martingale, because if you consider the conditional expectation of each multiplicative factor, given the history, then assuming that YT is IID, this will become mu, right, the true mean. And if we plug in mu in place of nu, this will be mu, so it will be canceled out. So what we end up getting is b plus 1 minus b, which is 1. So meaning that it should be martingale. And given this martingale sequence, we know that by Weyls inequality, which is martingale counterpart of Markov's inequality, we know that this sequence must not exceed the threshold 1 over delta with high probability over the entire time horizon. So this is a stronger guarantee actually than what we need. We only need that Gn of mu is less than 1 over delta, but out of this construction, we can actually achieve a stronger guarantee. Okay, so now I owe you the interpretation of this potential function as a cumulative wealth from a synthetic two-stock market setup. So here is how we can construct. Okay, so we consider a two-stock market where there exists cash and a stock, and there exists some investor. And so at day T, at the beginning of the day, the investor will choose like which proportion he's gonna like distribute his wealth to cash and stock. So if you chose BT from between 0 and 1, then cash he puts BT and 1 minus BT on the other, and at the end of the day, the investor will get how much the price changes over the day. And for cash, if there is no interest, it will be just 1. And for stock, we can design the stock market such that it depends on YT over nu. Okay, so the stock market depends on the choice of nu. Then what we can say is that over this day T, the multiplicative wealth, the multiplicative gain of the investor is BT times 1 plus 1 minus BT times YT over nu, which is this. So if this investor starts from $1, then you can easily show that this product is the cumulative wealth of this investor at day N. Okay. So I mentioned semi-unbounded coin betting in the earlier slides, and this is what I mean by semi-unbounded coin betting setup. So this is not actually coin betting, but yeah, historically people call it coin betting. So yeah, we use the name of coin betting, but this is actually a stock market. And some historical bits is that like this type of betting framework was studied and proposed under bounded variables. And for this non-negative unbounded random variables, this Wadby-Smith Ramdas at 2022 proposed this construction in this guise, but this two-stock market formulation is from a paper, one of my paper with Alankritabad, and there exists also a K-stock market variation for bounded vectors. So this type of gambling setup can be adaptive to different random variables with different dimensions or constraints to result in some new concentration inequalities or confidence bounds. All right, so now combining this idea of betting and the testing, we get this template to get a lower confidence bound. So given a causal betting strategy, so this betting strategy can depend on the history. This will induce the wealth function from the two-stock market I just described, which might look like this. Then you can construct a lower confidence bound by testing with this function. Okay. So like in practice, this root should be computed by some root finding algorithm, but this can be done in some like moderate complexity, like using bisect algorithm or some faster alternatives. So this is not a big deal. But the remaining question is like what strategy to use. Right? So we want to deploy a better betting strategy such that this wealth function as a function of nu might be much larger than others. Right? Because if we have this red line as a potential function, then this will lead to a tighter LCB. Okay, so it all depends on which betting strategy we are going to use. So I'm going to talk about what betting strategy to use in the next slides. Is there any questions so far? All right, so now the remaining question is what strategy to use. So the simplest strategy we can think of is the so-called constant rebalance portfolio, which redistributes the wealth at each day by the same proportion. So there exists some argument to justify why we need to care about the constant rebalance portfolio considering the IID stock markets. But yeah, if you're interested in, you can ask a question later. But yeah, considering the class of constant rebalance portfolio is rich enough, I will show you. And let's say let's denote the wealth of the CLP with B factor like this. And then this is an illustration of the performance of CLP over time. So let's say B is 0.1, then as you collect more and more samples, then you can make more and more money. This dashed line is the true mean. And the lower confidence bound constructed by this is getting closer to the true mean. And if you sweep this different V values over 0 and 1, then you can see that different Bs there's no single B that achieves the best performance over time. So what's tempted to do, therefore, is to track the maximum wealth of CRPs, which is the frontier of this plots, in hindsight. So can we actually track this this maximum of all the CLP wealth in hindsight? And the answer is yes. So this can be achieved by the celebrated Kover's universal portfolio, which is defined as mixture wealth. So the universal portfolio's wealth is defined as the mixture of all CRP wealth with respect to some mixture distribution, which is typically chosen as the beta half-half prior. So this is a kind of Bayesian mixture, you can imagine. And Kover and Ordentlic show that this is minimax optimal, and the discount factor is like 1 over square root of t, which is polynomial. And with this discount factor, this mixture wealth is following the performance of the best CRP. Okay.
Can I ask 2 questions?
Sure.
Just interrupt us. Why does the betting strategy have to be causal, as you mentioned?
Oh yeah, so it has to be causal to make this wealth sequence martingale. So if you consider taking expectation over expectation given the history, the conditional expectation given the history BT and 1 minus BT will be constant if this were causal. But if BT is looking at the future, then the conditional expectation becomes non-trivial.
If I had a fixed data set size n and I only wanted to make a confidence set for that size n, do you still need to do this, or is this about the time uniformity?
Yeah, that's a very good question. Because of this construction, there is a logarithmic factor in our bound, which is an extra factor. But so you might be tempted to try to construct confidence bound only for this specific time step, but that's surprisingly difficult. So this gives a very simple construction of the lower confidence bound with the notion of gambling, but yeah, it's not very straightforward to do so directly. But there exists some recent work that tries to get rid of the log n factor.
hypothetically, if you didn't restrict yourself to causal betting mechanisms, there could be a better, like a tighter confidence bound?
I think the difficulty comes from the fact that that doesn't fit into this desiderata. So like it has to be like small when mu is when the function is evaluated at the underlying function mu. So it's again tied to the fact that it's a martingale. But if you use some function, strategy that is looking at the future, that is able to look at the future, then you might make more money even if mu is equal to mu. So yeah,
because algorithmically your algorithm just gets all of the data at the same time because it's just offline, right?
Yeah. Right. Yeah. Right. But yeah, your point is
Okay.
very valid, and yeah.
All right, thank you.
Yeah. Thanks. All right. Okay, so yeah, so this idea of using universal portfolio in constructing a confidence bound was first explored by Orobana and John. And I also have some works on like the variation of this for bounded random variables and multi-dimensional vectors as well. And this work is about applying this universal portfolio on the unbounded random variables. Okay, so at the end of the day, what we get is this UPLCB, which is the combination of application of covers universal portfolio onto the semi-unbounded co-embedding setup. Okay, so in practice, what we will need to compute is either this mixture wells or this penalized version of maximum wells of CRP. But we recommend to use this penalized version because to compute the mixture wells exactly requires some dynamic programming, which ends up, incurring this quadratic complexity. So here's the main theorem. So what we can show is the following. So with high probability, this gap between the lower confidence bound constructed by universal portfolio is upper bounded by the variance of the underlying process, square root of the variance. Yeah, and this inequality is just because like this is a better strategy, and this is lower bounding. So lower confidence bound will be slightly loose, but yeah, but I'd like to remark that in practice, you might be tempted to use this penalized version because of the computation complexity. And also during the proof of this theorem, we rely on the, we analyze this universal portfolio by analyzing this relaxed version. So it has two like dual roles in this picture. And as a result, like as a corollary, we can, we can prove the variance adaptive selection guarantee I presented earlier immediately. It's very straightforward from this lower confidence bound guarantee. All right. So this was about construction. So the are some experiments. So to evaluate the performance of this UPLCB, we consider the synthetic reward processes with infinite force moments. So this is kind of made up setup just to demonstrate how it performs and how empirical Bernstein performs. So the sample, so this was done over like 100 different trajectories. So this is a sample mean with standard deviation, and empirical Bernstein behaves like this pretty badly. The convergence is very slow. And I alluded to that this Watby Smith et al. has an idea, proposed the idea of this stock market construction in disguise, but the proposed algorithm there has some hyperparameter, sigma naught squared, and they don't have rate guarantee. But if you sweep different sigma naught squared, then you can see that there exists some sensitivity issue with the hyperparameter. And logarithmic smoothing performs like this, whereas our universal portfolio LCB performs the best with theoretical guarantee. So fairly speaking, like if you know how to choose Watby Smith et al.'s algorithm, the hyperparameter there optimally, then it can be quite good. But yeah, it requires some tuning. And we also have some experiments on the policy selection problem with pessimism using the experiment setup from Wang et al. So basically, we compared ours to logarithmic smoothing and empirical Bernstein, and you can see that, our performs the best, or either best or statistically indistinguishable from the best. So underlined ones are the best, and the bold ones are statistically indistinguishable ones. All right, so for the rest of the talk, I will just briefly go over the policy learning setup.
Can I ask some clarifying questions again?
Sure. Yeah.
Could you go back to the slide where you gave the results for the confidence bound?
Yep.
Yeah. So this, you were explaining, just to make sure I understood how it worked, you were explaining that you estimate the mean of some sequence of random variables yt.
Mm-hmm.
So in the policy selection case, are you taking this sequence to be like, for a fixed pi, you take pi over pi 0 times the reward, and that's the sequence that you're estimating the mean of?
Yes, that's correct.
Okay, and then you do this for every pi.
Yes.
And then take the maximizing pi when you're doing policy selection.
Yeah, so we will need to do this union bound over all policies. Yeah.
Is there computationally this requires estimating the mean of every policy simultaneously? Is there a way to do this that's not just like linear in pi computationally?
Excuse me. Right. Yeah, but different policies will give you different y's, like different y sequences, right? So I think it's hard to avoid the linear complexity in the policy class size. If that makes sense. Yeah, I don't think there is a shortcut unless there is some structure in the policy class.
Yeah, or the reward class.
Yeah. Right. Yep, thanks. Right. Yeah, if there is no other question, I will just briefly go over the second part. It will be like 3 slides. All right, so as I alluded to earlier, now if you consider learning or optimization, then the policy class is infinitely large. So this could be very cumbersome. But given the construction we saw for the all policy selection problem, you might be tempted to think about LCB-based pessimism, right? But but there we require some root finding, procedure. But that can be handled, that can be formulated in terms of optimization as follows. So this, if you think about the penalized maximum wealth, and it's about finding new, that makes this 0, and that can be formulated as this maximum over alpha and mean over mu. optimization. But obviously, solving these optimization problems in practice will be very hard. So this is not very desirable. So in the literature, people assume that people assume some oracle efficiency to tackle this problem. So assuming that the objective function is nice enough such that we can assume some oracle efficiency and to argue regret guarantees on top of the assumptions. So oracle efficiency means that, given the objective, it's optimizable efficiently with a given optimization oracle. So it can mean different things in different contexts and setup. So in our paper, what we propose is a family of objectives achieving the state-of-the-art guarantee. So the form of the objective function is like this. So it's a summation of over phi of some beta hyperparameter times the importance weighted reward, which could be like, tempting if you consider stochastic optimization of the neural network policy and stuff. Like, if pi is differentiable, then you can think about you can ensure the differentiability with respect to pi, theta parameter, the parameter of the policy and stuff. So this is something desirable in this learning setup. And the key observation here is the following. So pi is some design function we choose. And for any function pi that satisfies this property, so like this is a lower envelope and this log 1 plus x is an upper envelope. So these are some pictorial visualizations of the lower envelopes with different choice of C1 and C2. So whatever phi function that lies between in between this upper and lower envelope, they implement a sort of pessimism. So it implements, in other words, it underestimates the true value. So so as a special instance of this this class of design function phi, the logarithmic smoothing falls into the class, obviously. And we can do a little bit more aggressive thing by considering what we call freezing. So here we introduce this thresholding function such that if the importance weighted reward is too large, then we just kill that off because that will incur too much variance in the estimator. So it more aggressively reduces the variance in the estimate. So it could be advantageous with small sample size, as we will demonstrate the effect in the next slide. Right, so this is what we call freezing. And in terms of theorem, we can show the optimality guarantee, the guarantee on the optimality gap in the following sense. So here, f beta phi is some non-negative value, which we call negative influence. So larger the better, like larger negative influence will make this gap smaller. And we can show that this freezing is giving you larger negative influence than logarithmic smoothing. So in general, like this has some effect in reducing the optimality gap, but we don't have a more finer theoretical guarantee regarding the subtle trade-off between bias and variance. But yeah, so this is our theoretical guarantee about freezing. All right, so this is the experiment we demonstrated to use to demonstrate the effect of freezing. So the blue one is the logarithmic smoothing, and the freezing is on top of the logarithmic smoothing, the sky blue one. And you can see that if the data size is small, then the effect of the knocking out potentially large variance data points are very crucial compared to the logarithmic smoothing as expected, but the performance in the large sample size get diminished, which might be also expected. But yeah, but this shows that aggressively knocking out potentially high variance data sample points could be beneficial in the small sample regime. All right, so let's conclude the talk. So I talked about the two techniques, batting and freezing for off-place selection learning, which result in improved second-order bounds for optimality gap. And in general, I believe that this efficient offline learning will become increasingly important. And some interesting future research directions could be, as I mentioned, in the off-policy learning setup, batting type idea is hard to implement, but can we come up with a way to bake into this batting idea for infinite policy class? And another question could be in a more general reinforcement learning setup, whether we can do a similar type of sophisticated techniques to have a refined theoretical guarantee better than the worst case ratio dependent bounds. All right, so this is all I wanted to share today. So thanks for your attention.
Thank you. Nice presentation.
Thanks a lot. Great
Yeah,
talk.
thanks a lot for staying till the end. And yeah, I hope things were accessible.
Yeah, it was a very
Yeah.
clear talk.
Yeah, it was very clear.
I just get to one question. If I understand correctly, when the policy class is infinite, your method is this new hyperparameter beta, right? That when the policy was finite, you didn't have. And in your experiment, how important was it? Did you observe that your method was quite robust on the choice of beta? Or do you have any comment on that? I was wondering.
Yeah, I think that's a good question. Yeah, unfortunately, I don't remember the experimental details, how we chose beta, but I'm pretty sure that so we swept over a grid of betas, and then there was some selection. Yeah, there was some selection step, using some validation split. So yeah, what we present here is after choosing the hyperparameter, and then okay. So I think what we did is the following. So we swept over different betas, and then given the resulting policies, we found the best beta for each method, and then we just use the best beta based on the selection results, and then report the results here.
I see.
So back to your question, I don't have a good idea on how different results we got with different betas.
Okay, nice. Anyway, it seems very important to make it adaptive.
Right.
Another question I'm a bit curious about, in your slide 18, I think maybe you have the proof of the theorem, if I remember correctly.
You mean this theorem?
Exactly, this one. So you said that even in the proof, you only use basically the maximum wealth in the proof, and you have this second inequality in your theorem. Do you have any thoughts if you avoid this inequality, if you can get any better bound? Using basically as mean estimate the wealth from covers universal portfolio itself with the mixture.
Yeah. Yeah, so that's a good question, but yeah, we don't know. Like, we don't know how to analyze this directly. Yeah. Yeah, but if you, so in our paper, we show how much they are different, like between this and this. Yeah, they are quite close, like, and yeah, I don't think they, even if it's possible to analyze this universal, the mixture wells directly, I don't think the gain would be really significant. Yeah, this is a quite tight bound, so.
Okay.
Yeah.
Thanks. Very insightful.
Thank you.
How sensitive is the confidence set to like the optimization errors in this like maximum?
Next
Like if you can't,
optimization.
because you're computing this maximum over the threshold B.
Oh.
Does it like mess you up if you can't actually compute this thing?
Yeah, that's also a good question. Yeah, so yeah, so right. So Kwangsong has this the implementation of this computing the maximum wells. So I don't know the exact detail how it's computed, but I think it's also computed in some numerical ways. And so I think you can set some like numerical accuracy you want to achieve, and yeah, within that accuracy you can like evaluate this function. And yeah, there might be it could be possible to like analyze the sensitivity with respect to the numerical accuracy and the resulting confidence bound by analyzing the slope of the wealth function you will achieve. But yeah, we don't have a quantitative result with that. Yeah. Right. But yeah, good point. Yeah.
I have another question, which is maybe more speculative, which is that like the confidence sets seem one-sided. So I guess I'm wondering if you could do the same techniques for optimism, or if it's just pessimism.
Right. So if you don't have the if you don't have an assumption on the boundedness or the upper tail of the random variable, then yeah, we don't know how to construct the upper confidence bound. But what we can do is the following. So I alluded to, I briefly mentioned that we can also achieve the same idea of betting confidence bound for evaluation, right? So for evaluation, we need both lower confidence bound and upper confidence bound. And the way we can do to construct the upper confidence bound is to exploit the fact that the underlying reward is, R is actually between 0 and 1. Then, and we know that the true mean is also between 0 and 1. Then we can still apply the same construction by constructing I will just be precise. So we the importance weighted reward is importance weight times reward, right?
Mhm.
And so for LCB, we apply the LCB construction on this importance weighted reward. But then to construct an upper confidence bound, what we can do is to consider this. Oh, sorry. So not this, but importance weighted 1 minus of this.
Right.
Then this will be UCB on this will give you UCB on 1 minus mu. I mean, yeah, sorry. You apply the same thing on this, which can be translated to UCB on mu.
Right.
So for this specific like construction of the YT, then you can exploit the structure and then construct the upper confidence bound, which can also implement the optimism. Yeah.
Don't you need the martingales to be non-negative?
Yes. Yes.
Would that? Oh, I see. But okay, you can't do the reweighting in this with this technique.
Reweighting meaning
like the density ratios, pi over pi 0 times reward.
Yeah. So the importance weight is multiplied on top of 1 minus reward, right? And
oh, I see. Okay, sorry. Yeah, I got messed up.
Yeah. So then the value, the expected value will be 1 minus mu. So yeah, we get.
Okay.
Yeah.
I see. And does that also give you state-of-the-art things for exploration in that case?
Oh, when we use this for online setting, you mean?
Yeah.
Yeah, we didn't think about that. Yeah, we haven't thought about that. Yeah.
I mean, that would be interesting.
Yeah, that's a good point. Yeah.
Okay, cool. Thank you.
Yeah.
Is there any remaining questions from anyone in the audience? Okay, then I guess if not, we can thank the speaker again.
Yep. Thanks a lot.
Thanks, John.
Thank you.
Yeah. Thanks for your attention and yeah. Thanks for the invitation. Yeah, it was really fun to have this talk. Yeah.
Yeah, thank you.
Great.
Yeah.
Thanks a lot. Amazing
Yeah,
talk.
bye. Yeah, thank you.
Bye.
Here we go. Bye-bye.
Okay. Well,
Good day, everyone.
enjoy the break, everyone. Thank you for coming.
Bye.
See you next time.
See you.
Bye-bye.